As this visualization of a sealing digital vault illustrates, keeping data secure starts with absolute boundary control. In modern hybrid infrastructure, API keys, database credentials, and certificates are often scattered across servers in plain text. If an attacker breaches the network, they gain immediate access to these raw credentials, allowing them to move laterally through the system. Securing these assets requires a centralized secrets management service built on a strict zero-trust model. Instead of trusting the internal network, the system assumes all traffic is hostile until a client's identity is cryptographically verified. The core of this architecture is the cryptographic barrier, a highly secure, volatile memory partition where all cryptographic operations take place. The absolute operational rule of this barrier is that no plaintext secret is ever exposed on the physical host server, and no plaintext is ever written directly to a persistent storage disk. By forcing all secrets to exist only within this transient memory space, an attacker who steals the physical hard drives or clones the storage database still retrieves nothing but encrypted, unusable data. This flow diagram illustrates multi-tiered envelope encryption, the mechanism protecting data moving into storage. Inside the barrier, a data encryption key, or DEC, uses the AES-256 GCM cipher to encrypt the actual secret payload, turning plaintext into ciphertext. The system must store this DEC to decrypt payloads later, but storing it in plaintext in the database creates a critical vulnerability. To solve this, the architecture introduces a key encryption key, or master key, designed solely to encrypt the DEC itself. When an authenticated client requests the secret, the process runs in reverse. The master key decrypts the DEC, and then the DEC decrypts the ciphertext, all happening exclusively within volatile memory. Ultimately, envelope encryption isolates the massive volume of daily data encryption from the system's singular root of trust. If a single administrator controls this master key, the entire system relies on a single point of human compromise. To prevent this, the secrets management system starts in a sealed state. When booted, it has no access to its own master key and cannot initiate the cryptographic barrier. This diagram illustrates protecting the root of trust, using Shamir's secret sharing to fracture the master key into distinct shares. To boot, operators use the /sys/unseal API, submitting a predefined threshold, like 3 of 5, to reconstruct the key and open the barrier. In automated enterprise environments, this manual unseal process is often replaced by auto-unseal mechanisms, which use an external cloud hardware security module to securely wrap the internal keyring. By distributing the key shares across different stakeholders, the architecture mathematically eliminates a single human point of failure in the authentication chain. Beyond storing static secrets, this architecture provides cryptography as a service directly to applications through its transit secrets engine. Instead of writing their own encryption logic, an application delegates the task by sending a plaintext string over a TLS encrypted connection to the /transit/encrypt endpoint. Looking at this interface, you can see the specific output returned to the application. The system encrypts the data and sends back a ciphertext string containing a version prefix, in this case, vault:\v1. Because this exchange happens entirely within the centralized service, raw cryptographic key material never touches the application to your container. The application simply takes the resulting ciphertext and stores it in its own database, shifting the burden of securing the encryption key back to the central vault. This architecture offloads the complexity and liability of cryptographic implementation from individual developers to a hardened central service. The National Institute of Standards and Technology Publication 800-38D dictates that AES GCM keys should be rotated before reaching approximately 4 billion encryption operations. Traditionally, rotating a master encryption key causes operational bottlenecks. It requires locking the database, pausing all read and write requests, and manually re-encrypting the storage layer. This diagram demonstrates solving downtime using a versioned internal keyring. Calling the rotate endpoint generates a new v2 key while retaining v1 in memory. New incoming data is automatically routed to and encrypted with this latest key version, outputting a string prefixed with vault:\v2:. By retaining the older keys in memory, the system can still seamlessly decrypt legacy ciphertext that was encrypted under the original v1 key. To proactively upgrade older data, applications can use the /rewrap endpoint. They send the v1 ciphertext to the vault, which decrypts it and returns it re-encrypted under the v2 key. This entire rewrap process happens strictly within the cryptographic barrier, without ever exposing the underlying plaintext to the network. Versioned keyrings enable continuous security compliance, allowing the system to update its encryption logic without breaking access to legacy application data. The ultimate architectural challenge is synchronizing a newly rotated master key across a distributed, high-availability cluster without causing downtime. In a high-availability cluster, the active leader node initiates rotation by generating a new active key, key n+1. The leader encrypts this new key using the previous key, key n, creating a short-lived upgrade key package published to the shared replication log. The follower nodes constantly monitor this replication log, waiting to ingest the new upgrade key. Because the follower node already holds the old key n in memory, it simply unwraps the package and extracts the newly generated key n+1. The follower then appends this new key to its own internal keyring, achieving complete synchronization with the leader node. Upgrade keys enable seamless online key transitions across clustered nodes. The entire cluster rotates its root of trust without manual unsealing or system pauses. Decoupling the data encryption keys from the master key restricts the primary cryptographic risk to the volatile memory partition. Distributing the root of trust via Shamir's threshold unsealing ensures that no single individual can compromise the entire service. As the completed flow shows, versioned keyrings and replication log upgrade keys automate key rotation as a background task. This design secures sensitive data through a continuous cycle of rotation and distributed trust, ensuring that protection remains consistent across distributed infrastructure.